Commerce on the internet has a structural limitation. Every electronic payment relies on a financial institution as a trusted third party to process the transaction. Because these institutions act as mediators, they can't avoid dispute resolution. That mediation increases transaction costs, which limits the minimum practical size of a transfer. It also makes completely non-reversible transactions impossible. With the possibility of reversal, merchants are forced to be wary of their customers, demanding excessive personal information just to approve a sale. In the physical world, we avoid these costs by handing over cash. The transaction is final and no middleman is required. But over a digital communications channel, that direct peer-to-peer exchange hasn't existed. In 2008, Satoshi Nakamoto published a white paper proposing an alternative, an electronic payment system based entirely on cryptographic proof instead of institutional trust. To make that work, the network had to solve a specific vulnerability called the double spending problem, guaranteeing that a user cannot spend the same digital token twice without relying on a central mint to verify the record. The white paper begins by structurally defining an electronic coin simply as a continuous chain of digital signatures. To transfer a coin, Owner 1 digitally signs a hash containing the previous transaction and Owner 2's public key. That hash is appended to the coin's data structure. The payee can cryptographically verify these signatures to read the exact history of ownership. However, examined in isolation, this mechanism has a fatal flaw. While the chain of custody is mathematically valid, the payee has absolutely no way to verify if a previous owner signed an earlier duplicate transaction with someone else. Digital signatures provide strict control over ownership. But as a currency, they fail if the system still requires a central authority to look at the ledger and determine which transaction arrived first. Without a central mint acting as the ultimate arbiter of time, the only way to confirm a transaction's validity is for the network to be aware of all transactions simultaneously. Nakamoto proposed a strict rule: all transactions must be publicly announced, broadcasting out to an unstructured peer-to-peer network. To agree on the chronological order of those incoming broadcasts, the system uses a decentralized timestamp server. The server groups pending transactions into a single block, takes a cryptographic hash of that entire block, and widely publishes the alphanumeric string. To create continuity, every new timestamp explicitly includes the hash of the previous timestamp, locking them together. This chaining process forces an objective timeline. The data had to exist at a specific moment to be included in the hash, effectively solving the sequencing problem without relying on a human mediator. But a decentralized network still requires a mechanism to reach a majority decision. If consensus relies on one IP address, one vote, an attacker could easily subvert the ledger by allocating thousands of fake IP addresses. The solution is to tie the vote to a physical thermodynamic cast. The network enforces a strict one CPU, one vote system. This is achieved through a proof-of-work mechanism. Nodes must compete to scan for a specific value that, when hashed with the block's data, produces an output starting with a required number of 0 bits. In this block header, nodes repeatedly increment a random number, called a nonce, running the calculation over and over. The node rapidly cycles through unpredictable variations until it expends enough computational effort to hit a valid string of leading zeros. Once that immense CPU effort is expended and the required zeros are found, the block is locked. If an attacker wanted to alter a historical block, they would have to completely redo the proof of work for that specific block, and then recalculate the work for every single block chained after it. The longest chain represents the majority decision, proving mathematically that the record originated from the largest pool of honest computational power. In practice, the network operates in a continuous loop. Nodes collect transactions, dedicate their CPU power to solving the mathematical puzzle, and broadcast the finished block to their peers. Nodes follow a strict rule. They always consider the longest proof-of-work chain to be the correct one, and actively dedicate their resources to extending it. If two nodes solve a block at the exact same time and broadcast different versions, the chain splits into two divergent branches. Individual nodes will simply work on whichever version they received first, while temporarily saving the alternate branch in memory. The tie is naturally broken when the network finds the next proof of work, extending one of the branches further. The nodes working on the shorter branch immediately abandon it, migrating their computational power back to the dominant chain. This means the network operates with almost zero central coordination. Conflicts resolve autonomously through the sheer accumulation of computational weight. This raises the ultimate security question. If a dishonest sender secretly works on an alternate chain to reverse a payment they just made, how long must the recipient wait to ensure the transaction is permanent? The white paper models this race between the honest chain and the attacker's hidden chain as a mathematical binomial random walk. The probability of an attacker catching up from a deficit is identical to the classic gambler's ruin problem in probability theory. This chart graphs the attacker's success probability, P, against honest blocks added, Z. As the network advances, the attacker's odds drop in a steep exponential decay. At 10% computing power, the rewrite probability falls below 0.1% after just 5 blocks. Transactions are never formally locked by a human administrator. Instead, they achieve probabilistic finality, becoming computationally impractical to alter as the chain grows deeper over them. By combining digital signatures with a decentralized timestamp server and cryptographic proof of work, the architecture creates a resilient, leaderless consensus. It replaces institutional trust with a mathematical guarantee of history.